Well, thank you, Elizabeth, for that introduction, and hello, everyone. I'd like to begin by thanking Elizabeth, Emma, and other members of the organizing committee for inviting me to participate in this plenary session and for the very special opportunity of delivering the keynote address. I'm so happy about the emphasis on transformations in this year's conference and the expressed ambition of the society to transform in ways that make it more inclusive, equitable, and better able to respond to global freshwater challenges. So let's go with that. You'll see from the title of my presentation that I'll take a world or global view on one of the most fundamental and ubiquitous challenges facing freshwater ecosystems, which is protecting the water they need in a world of increasing water demands for other purposes like agriculture, energy production, and domestic or industrial uses. Clearly, I'll be talking about the science of environmental flows and the challenges and opportunities related to it. But the message I'd like to deliver goes beyond the role of environmental flow science to consider us as a world community of people intent on applying science to achieve a goal. That's where the Society of Freshwater Science's ambitions to transform in ways to become more inclusive and equitable come in. The ambitions of the Society are also, or at least they should be, the ambitions of the entire global community of freshwater scientists and practitioners. But becoming more inclusive and equitable requires real action, changes in the way we conduct our research, and even changes or at least flexibility in our own logic and worldview. Elizabeth's introduction gives you a sense of who I am, but let me say a bit more about where I work so you know where I'm coming from. IHE Delft Institute for Water Education is a knowledge institute with the mission of working in partnerships to strengthen capacity in the water sector to achieve global sustainable development. We look a lot like a college or faculty in a typical university, with different departments and offering MSc and PhD degrees. But as our mission suggests, we're also focused on achieving the goal of global sustainable development. A big goal for an institute with just over 100 academic staff. That's why working in partnership is ingrained in our mission and our identity. We're also affiliated with UNESCO, the United Nations Educational, Scientific, and Cultural Organization. We're one of numerous water centers around the world supporting UNESCO's mission of contributing to the building of a culture of peace, the eradication of poverty, sustainable development, and intercultural dialogue through education, the sciences, culture, communication, and information. We also maintain our own expansive network of partner institutions, including universities, government agencies, NGOs, and even a few private sector companies. So we're right in the thick of collaborative efforts to address global challenges. But we also struggle to make our institution and activities more inclusive and equitable, so as to be more effective in our actions. We're on the same path as SFS, and probably many of the institutions you all represent. We all need to transform. So let's begin, and first focus on the challenge. Many of Earth's natural freshwater ecosystems are drying up, and many more have seen their volume of water altered in ways that degrade habitat conditions and reduce their availability, causing unnatural stress on aquatic biota. Now, I realize freshwater ecosystems are subject to a wide range of stresses, including pollution and overexploitation of biota, but I'd like to focus on the volume or magnitude of water available to freshwater ecosystems because that magnitude literally determines the entire volume of space available to aquatic organisms. I mean, think about it. Their habitable world extends only to the three-dimensional limits of the river or lake or wetland water volume. Inside that volume, aquatic organisms must carry out all the functions of life. They must be born, eat, and grow, find shelter, and reproduce. To create the next generation, they need space to carry out these functions and interconnected habitats that are suitable for each and available at the necessary times of year. The image on the left is of the Guadalupe River, which flows through San Jose, California, and empties into San Francisco Bay. In times of drought, 100% of the river's water is retained in reservoirs to supply mainly agricultural water needs. At least that's what it was in 2015 when this photo was taken. The water needs of freshwater ecosystems were of lower priority, and the consequences were terminal. Of course, the quintessential example of disappearing inland water in aquatic ecosystems is the Aral Sea, although it's brackish, not exactly freshwater. The Aral Sea was reduced in size by 90% over the past 50 years, due mainly to upstream agricultural water diversions. This led to the nearly complete destruction of native aquatic plants and animals and the loss of related ecosystem services. Lake Chad in West Central Africa is another well-known case. Lake Chad has also experienced huge fluctuations in size, including 90% shrinkage, but mainly due to climate variability and climate change. The consequences to freshwater ecosystems, however, have been no less severe, and the impacts on dependent human communities may have been even more severe. There are so many examples of drying lakes from nearly every part of the world. The causes are diverse, but human interventions in diverting water to other uses or changing climate are common to most of them. Rivers are also drying up, especially during the dry season in drier climates. The Darling River in Australia has been in the news in recent years and served as a flashpoint for hard discussions about water management decisions in the Murray-Darling Basin. Again, a combination of drought and upstream agricultural water abstractions are the main causes, and the Murray-Darling Basin has some of the most advanced legal, scientific, and infrastructural capacity to define and deliver environmental flows. But even then, we see it's not always enough to protect water for ecosystems. So many other rivers, large and small, are subject to the same unnatural seasonal drying. The Indus of Pakistan, Colorado of the USA and Mexico, Pilcomayo of Paraguay and Argentina, and the Yellow River of China. But as most of us already know, rivers need not become completely dry to experience severe ecosystem impacts. Large alterations in seasonal, annual, and interannual variability of river flow magnitude may also have severe detrimental effects. This is the Flaming Gorge Dam and reservoir of the Green River, a headwater tributary of the Colorado River. The stored water is used for hydropower generation, irrigation, and recreation. In the plot, the blue line is the river's flow regime before construction of the dam, when gentle low flows dominated from September to March, providing slack water environments for riverine biota to minimize energy expenditures and survive the winter months. While during the summer, flow magnitudes peaked, cueing important life history events, creating gravel beds necessary for spawning, activating floodplain habitats, and rejuvenating the riverbed. After the dam was constructed, the flow regime became more uniform, doubling wintertime flows and effectively erasing the summer high flows. With millions of dams blocking rivers throughout the world, and most operated to meet objectives other than protecting freshwater ecosystems, this form of volume, magnitude, and regime alteration is becoming universal, degrading natural ecosystems and forcing them into new hybrid and increasingly novel states. And then there's the loss of natural wetlands, which are also disappearing due to diversions of inflowing waters as well as widespread drainage and reclamation efforts. The black and white graphic on the left shows an estimate of percent wetland loss per state in the USA since the late 18th century. And the pie chart shows the cumulative loss for the lower 48 states, indicating a decline in wetland area of more than 50%. Now, these are pretty good data from the USA, and we have decent data sets from some other countries as well, but not for most of the world. This highlights a particular challenge for those of us in the global scientific community, those interested in the global fate of freshwater ecosystems, and not only those in our own state or country. Data and knowledge about the extent and specifics of freshwater ecosystem loss and degradation remain strongly case-based and country-specific. This table is from Ramsar's 2018 Global Wetland Outlook Report, indicating the global area and ideally change in area of different inland natural water wetlands. Note that numbers for percent change are reported only for peatlands. All of the other empty shaded cells indicate no information available at the global scale. Only qualitative trends can be identified. We lack the knowledge to effectively inform protection and restoration efforts in many parts of the world, and and it's often in data-poor parts of the world where freshwater ecosystems are experiencing most strongly new and accelerating pressures on their water availability and natural regimes. I could go on and on presenting cases of drying freshwater ecosystems and alteration in natural hydrological regimes, but I know these problems and challenges are clear to all of us. I've also not presented anything about the actual impact on freshwater ecosystem condition and integrity. But I believe most of you will also be aware of those impacts in your areas, and we will be familiar with the alarming 85% decline in the population size of freshwater species reflected in the Living Planet Index, and the high proportions of endangered species documented in IUCN's Red List. So let's transition from a focus on the problems and challenges to opportunities, although the two really cannot be completely disconnected, and I'll continue to go back and forth a bit. So let's begin by looking at progress in assessing and mapping global trends in extent and condition of freshwater bodies, as well as some of the pressures influencing them. Assessments at the global scale are of enormous value for revealing global patterns and trends and informing dialogue, discussion, and agenda setting at the global scale. But they, of course, do not provide the detail and resolution needed for actual management decisions and actions on the ground. There's another level of analysis required for that, which we'll also come to. But let's have a look at some of the exciting and relevant research happening at a global scale. This slide shows the results of a global analysis mapping changes in the extent of inland and coastal surface water in a 32-year period between 1984 and 2015. The results are not very visible on the map, but they do stand out more prominently in the curves following latitude and longitude around the world. The dark and light red curves indicate the loss of permanent and seasonal surface water, respectively, and the dark and light green curves indicate new permanent and seasonal surface water. In total, the authors report a loss of almost 90,000 square kilometers of permanent surface water, over 70% of which occurred in the Middle East and Central Asia. The authors linked these losses to drought and human actions, including river diversion or damming and unregulated withdrawals. Perhaps surprisingly, after the first 10 minutes of our talk, they also report 184,000 square kilometers of new permanent surface water bodies. But these increases they attribute primarily to the creation of new reservoirs, although climate change is also cited. These results are based on the analysis of 3 million Landsat images at 30-meter resolution, providing a methodologically consistent approach to quantifying surface water area and change around the world. But of course, many details of these surface water bodies remain unknown, and methodologies using remote sensing and especially satellite data to analyze surface water bodies continue to improve, especially with the new Sentinel-2 satellites. There are also numerous efforts underway to construct useful global data sets from extensive review of the peer-reviewed and gray literature, including governmental reports. One such product from this analytical approach is the WET database, consisting of 306 data sources. The geographic distribution of sites for which data were obtained are shown on the map and identified as referring to marine and coastal wetlands, human-made wetlands, and other inland wetlands. The assembled data set enabled the authors to discern 2,130 individual time series records of change in wetland area from local sites, which they aggregated to national trends. These are reported for different regions of the world. The records show natural wetlands declined by 35% on average between 1970 and 2015. Again, excellent information to feed into a global discussion and help set international priorities. I was involved in this recent collaborative effort to map the world's remaining free-flowing rivers. The assessment examined the connectivity status of 12 million kilometers of rivers globally and identified those that remain free-flowing in their entire length. We found that only 37% of rivers longer than 1,000 kilometers remain free-flowing over their entire length, and 23% flow uninterrupted to the ocean. Importantly, this assessment distinguished between 5 different pressure factors, including river fragmentation caused by barriers like dams, degree of flow regulation influenced by the storage capacity of reservoirs, sediment trapping, water consumption, and urban development in riparian areas and floodplains. This enabled mapping of the distribution of dominant pressures as well. The pressure's water use and degree of regulation enabled the distinction between excessive withdrawal of water from river systems and potential alteration in flow regimes by large reservoirs. Both appear as dominant pressures in parts of the world, but the combination of dams and large reservoirs was found to be the most widespread dominant pressure. Great information and a step forward in understanding the distribution of pressures and their effects. But again, the specific details for each river reach are minimal, and the application of results is mainly limited to higher level strategic discussion and planning. The global assessment approaches we've looked at so far have been based on direct data collection using satellites or compilation and analysis of global data sets. They're focused on identifying the current status of inland water bodies and discerning trends. There's also been great progress in the development and application of global modeling approaches to examine the relationships between natural runoff in rivers, abstraction of water for different purposes, and consequences for environmental flow levels in rivers. I mentioned agricultural water demands multiple times in the talk so far, and most of you will know that agriculture is by far the largest consumptive user of water resources in rivers, lakes, wetlands, and aquifers around the world. Agriculture is therefore also the main competitor for ecosystems in the allocation of water resources. This is a modeling study published in 2017 by Jägermeier et al. A global runoff model is used to reconstruct natural flow regimes of the world's rivers. 3 different hydrological approaches to determine environmental flow requirements are also applied and the mean taken. Considering current water withdrawals for irrigation and other uses, the authors then analyzed the impact of environmental water levels in rivers when agricultural water demands are prioritized, as we've seen they regularly are, as well as how much food production might be decreased if environmental flows are prioritized. They found that 41% of current global irrigation water requires tapping into environmental flows. And if environmental flows were to be prioritized, half of globally irrigated cropland would face production losses of greater than 10%. In Central and South Asia, where we know the problems are most severe, the agricultural losses are approximately 20 to 30% of total country production. This exposes the seriousness of the challenge we face in trying to meet food requirements while also protecting water required for ecosystem health. Okay, now a final example of progress on global scale modeling that opens up opportunities for better informed strategies and ultimately actions to protect water for freshwater ecosystems. The previous model results by Jägermeier et al. Illustrated the limitations of river flows to meet agricultural water demands. As this information influences policy and management decision making, a likely response is to look to other sources of water, such as groundwater, to make up the difference. But this 2019 modeling study by de Graaf et al. Concludes that groundwater pumping has already led to stream flows below environmental requirements in nearly 20% of the world's watershed. The simulation also projects that by the year 2050, unchecked groundwater pumping will lower stream levels below environmental flow limits in more than 50% of watersheds. While the results of this assessment further intensify the challenges, they're essential for framing the debate and confirming that if we want to protect and preserve freshwater ecosystems, if we want to achieve sustainability, significant and even revolutionary societal transformations may be required. This isn't going to be easy. Let's continue looking at recent research that significantly increased our ability to provide meaningful guidance to decision makers, focusing more specifically on water for river ecosystems. We know from the boundary conditions identified by global models that it's going to be very challenging to simultaneously meet the water needs of river ecosystems and other users But however difficult the implementation will be, it's crucial that we enter the process with reliable figures for the water requirements of ecosystems, quantified at scales that are meaningful for management. And the generally agreed scale for water resources management is, of course, the river basin or watershed. Good environmental flow methodologies focused on river reaches have been around for a long time, but it wasn't until 2010 in the publication of the Aloha framework that we had a conceptually sound approach for quantifying environmental flows at basin scales. The framework is holistic, incorporating hydrological, ecological, and social components. It consists of steps to establish a hydrological foundation, classify streams into ecologically relevant flow regime classes, and determine the degree of present or future flow alteration. It includes the definition of flow ecology relationships that relate a level of ecological condition to the degree of flow alteration. And finally, it incorporates the societal values that ultimately decide the acceptable ecological conditions to be targeted, thereby setting limits on the degree of allowable flow alteration. It's a coherent yet flexible framework that can be adapted to different management contexts. But it did call for hydrological, ecological, and ecohydrological inputs that were not available in 2010, at least not widely available. So over the past decade, it's also been a framework for research, and the scientific community has made great strides in developing methods and conducting the analyses necessary to apply the framework. Let's have a brief look at some of those developments. Determining baseline hydrographs for the hydrological foundation was already well within the abilities of the hydrological community, whether using existing hydrological records or model simulations. But the classification of rivers into ecologically meaningful regime classes required additional effort. The approach taken was to classify rivers according to similarities and ecologically relevant characteristics of the natural flow regimes. This wasn't especially difficult because the position of rivers within river basins and commonalities in topographic and climate variables were natural guides. The image on the slide shows a classification for rivers of Australia. In the zoomed image, note that the classes are distinguished by the stability or unpredictability of river base flows and their seasonality. River classes determined on basic variables such as these will also share other ecologically relevant characteristics in common. Classifications such as this have now been made for basins in many parts of the world. The resolution of global hydrological data and models may also enable a global classification at basin scale, but I don't think I've seen one yet. Determining the degree of hydrological alteration involves comparison of the present or potential future flow regime of rivers to their natural flow regime. An example of assessed hydrologic alteration for rivers in the state of California is shown on the slide. And these may also be aggregated according to river class, which is called for in the framework. Note that the direction of alteration may reflect either depletion or inflation of flows relative to natural. And as we saw with the Green River downstream of Flaming Gorge Dam, the river may have depleted flows in one season and inflated flows in another. The final product of the hydrological component of the analysis is a data set of hydrologic alteration per river class. The conceptual and methodological challenges in the ecological component of the framework have been more pronounced than the hydrological component. Ecologists must identify how ecological processes in their river vary in relation to different components of the flow regime, ideally those used to classify the rivers hydrologically. Because individual species may vary across rivers even within a common hydrological class, it's been suggested that species traits or guilds may prove more useful in transferring flow ecology relationships across rivers. Images on the screen are from a 2018 paper by Chen and Olden, evaluating the transferability of flow ecology relationships. Ecologists have been challenged even more in devising approaches to quantify ecological responses to incremental flow alteration. The images on the screen are from a 2018 modeling study by Hain et al., investigating the use of hydrologic models in conjunction with ecological data to develop empirical flow ecology response models. They evaluated their results using fish species richness as an indicator. Simulated degrees of change in richness are plotted in relation to different variables affecting the flow regime, including climate change, increases in impervious surfaces, and increased water withdrawals. Results indicate increasing changes in richness when pressures are combined. But more research and method development are needed to produce high confidence results suitable for full application in environmental flow assessments. This topic's at the leading edge of environmental flow research today, as is the topic of ecological responses in a continually changing, non-stationary world. So we've covered a lot of ground already, highlighting the need to protect water for freshwater ecosystems, reviewing select global scale studies, putting the problem in context, and setting boundary conditions, and reviewing advances in basin scale assessments to identify meaningful flow ecology relationships that can be used to quantify ecological responses to altered flow levels. Now it's time to bring people squarely into the picture. First, by considering the final step in the Aloha framework, and then by including ourselves as agents in the mission to transfer knowledge of environmental flow requirements into actions to protect them. In the end, environmental flows are just as much about people as they are about ecosystems. The social elements envisioned in the original Aloha framework were those governance aspects contributing to decisions about what are ecologically acceptable conditions in rivers. And governance aspects are indeed very relevant because they may also be linked to laws and regulations that lend power and priority to the protection of water for freshwater ecosystems. An example is the social process resulting in the European Water Framework Directive, which sets the common target of achieving good ecological status in the freshwater bodies of 21 different European countries. It's recognized that providing sufficient water to freshwater ecosystems is necessary to achieve good ecological status. But there's also an additional and growing field of research in environmental flows focusing on linkages between river flow and human well-being, spiritual needs, cultural identity, sense of place, and incorporating these linkages into environmental flows management. The rationale and contours of this exciting research area are described in the 2019 paper by Elizabeth Anderson and others, using multiple case studies. This enrichment of the scope of environmental flows is aligned with a newly expanded definition in global action agenda. And we may find that addressing these social needs is the most effective way of securing water for ecosystems in some situations. So let's continue to expand on the role of people in environmental flows and look at the global movement begun by environmental flow scientists and practitioners to find a collective voice and become more effective agents in bringing about the changes they wish to see. During the 10th International River Symposium and International Environmental Flows Conference held in Brisbane, Australia in 2007, attendees produced the first Brisbane Declaration and Global Action Agenda. This consensus document for the first time set a common vision and direction for environmental flows internationally, and it stimulated and steered a decade of research and expanded awareness of environmental flows globally. Then, in 2017, environmental flow scientists and practitioners gathered again in Brisbane to review progress made and refresh and expand the original vision and direction of environmental flows. This time, the international consultation process extended far beyond the attendees at the conference, and the revised statement and associated global action agenda grew to encompass more diverse views and actions. It was published in 2018. It includes a revised definition of environmental flows, expanded to apply to a broader scope of aquatic ecosystems and incorporating additional social dimensions. The consensus definition now is that environmental flows describe the quantity, timing, and quality of freshwater flows and levels necessary to sustain aquatic ecosystems, which, in turn, support human cultures, economies, sustainable livelihoods, and well-being. Providing these flows and levels is intended to meet combined ecological and social objectives. Now let's have a look at the Global Action Agenda. The Brisbane Declaration is summarized in 6 overarching statements, and for each, the Global Action Agenda includes actionable recommendations in the areas of leadership and governance, management, and research. The first statement makes clear that environmental flows are essential to protect and restore biodiversity, aquatic ecosystems, and the ecosystem services they provide for all societies. Governance and management recommendations call for the development of programs necessary to implement them, and research recommendations are for us as researchers to provide knowledge necessary for that implementation, namely to quantify flow ecology relationships and ecosystem services for all aquatic ecosystems that depend on freshwater, including groundwater-dependent ecosystems, and also to demonstrate ecological, economic, and societal benefits of environmental flows and healthy freshwater-dependent ecosystems in programs and projects. This includes a strong element of monitoring and adaptive management to revise actions as needed. Note that measured benefits should be assessed in the context of Sustainable Development Goals, reminding us of the global scope of the research needed. Narrowing our focus specifically to the statements and research recommendations, the second statement is that environmental flows are crucial to protect and restore the world's cultural and natural heritage, and the research recommendation is to improve understanding and quantify relationships between environmental flows, healthy aquatic ecosystems, cultural heritage values, and attachments to freshwater-dependent ecosystems. Elizabeth's paper and the working group it stems from are taking concrete steps in the implementation of this recommendation. And we're not beginning from scratch in this research. There's a wealth of past and present research on the relationships of people to rivers, but in many cases the dependence on flows and levels may not have been fully appreciated. The third statement acknowledges that environmental flows have been compromised, and today many aquatic systems around the world are at risk. And the research recommendation is to identify obstacles to implementation of environmental flows in different world settings, and to improve systematic planning tools and trade-off processes that can guide the location, design, and operation of water infrastructure for social ecological benefit. Note the emphasis placed on implementation mechanisms here. This is a call for us to expand our research beyond what are the flow requirements needed to sustain freshwater ecosystems and investigate why those requirements are not being implemented once determined. A sad fact of environmental flow science and practice is that there are large numbers of high-quality assessments of flow requirements that have never been implemented. The obstacles to implementation are rarely a lack of knowledge of what the environmental flow level should be. The obstacles are in delivering those flows in management programs. We need to better understand what these obstacles are and investigate means to overcome them. We need to incorporate elements of implementation science. The fourth statement is that implementation of environmental flows requires a complementary suite of policy, legislative, regulatory, financial, scientific, and cultural norms and values to ensure effective delivery and beneficial outcome. One research recommendation is to investigate existing and propose new mechanisms for integrating environmental flows implementation into broader water and related resource management systems. Often it's not clear where environmental recommendations and allocations fit into existing management systems. Where should they be embedded? A second recommendation is to research effective design, monitoring, and reporting of environmental flow implementation projects and programs, treating them as experiments where feasible. Now, this is the first explicit mention of action research approaches, although I believe they're implicit in nearly all research recommendations so far. We need to integrate our research into the implementation itself, working with implementers to experiment with different approaches to improve outcomes in a process of adaptive management. The fifth statement is that local knowledge and customary water management practices can strengthen environmental flow planning, implementation, and sustainable outcomes. The recommendation is to co-develop best practice models to ensure full and equal participation and respect for the responsibilities, rights, and systems of government of all cultures and stakeholders in environmental flow planning, assessment, implementation, monitoring, and adaptive management. This is a big one. Now, we'll likely all agree that things will be done differently in different places, and that there's useful information to be gathered from local people and their indigenous knowledge of the freshwater ecosystems. But this recommendation is not only asking us to be aware of those facts and listen to local people, it's asking us to be open to accepting the way things are done locally without trying to change them, and to accept other ways of viewing and conceptualizing the problems and solutions, even if they don't align with our own views and conceptual frameworks. We're being asked to embrace plurality and find ways to work together equally. This is profound, and I'm still working to fully understand and internalize it myself. It could fundamentally change the way we approach our science. And finally, statement 6 is that climate change increases the risk of aquatic ecosystem degradation and intensifies the urgency for action to implement environmental flows. And the recommendation is to conduct long-term studies of freshwater-dependent ecosystem adjustments and societal responses to changing flow and other environmental regimes in areas experiencing shifts in climate or human demographic patterns, demands for water. A second recommendation is to research new approaches to maintain and restore ecological resilience and societal benefits. This is another conceptual frontier in our science, asking us to transition from conceptual foundations based on stationarity to non-stationarity. Important insights into this research area have been published recently by Avril Horn, Leroy Poff, and others. So, that in a nutshell, is the Global Action Agenda on Environmental Flows. It calls for transformations, for us as a community to become active everywhere in the world, to tap into all of the advances in environmental flow research that I've reviewed and extend it further, delving more deeply into flow ecology relationships, better incorporating people and social processes, and engaging more directly in the implementation through action research carried out in cooperation with implementing agencies. In the final portion of this talk, I'd like to reinforce these points and look at a final set of opportunities for more effective international collaboration and action research. Virtually all research we do today is collaborative, and certainly most, if not all, of the research advances I've mentioned were accomplished in collaborative teams. Collaboration occurs within our own research groups and institutions and within our broader networks. Many of us also collaborate international. But we really need to make our collaborations global. Water needs to be secured for ecosystems everywhere in the world, and that means the research community needs to be engaged everywhere. Environmental flow science is an applied and problem-solving science destined for implementation in water resource management systems. We need to step up and take more personal responsibility for seeing that our science leads to implementation. And we can best do that by engaging with the implementers directly. Too many of us still view water resource managers and agencies as sources of data or as the audience for that final paragraph of our papers that presents management implications. Instead, we should increasingly engage them as research partners. My personal experience has shown that effective cooperation with implementing agencies makes my research questions more relevant, positively influences my research design, and helps me to present and deliver results in formats that can be quickly taken up and applied. So, working in partnership, conducting action research, and going global. What opportunities are out there to help us do this? Well, the largest opportunity is certainly in relation to Agenda 2030 and the Sustainable Development Goals. This global agenda has been officially adopted by 193 countries around the world, many of which have also aligned their national development and sustainability priorities with its 17 goals. Countries around the world now have a common structure and identifiable targets to work towards together. Many funding agencies have also adjusted their programs to finance the different measures identified. Environmental flows appear explicitly in SDG Target 6.4 on water use efficiently and implicitly in Target 6.6 on protecting and restoring water-related ecosystems. Let's have a closer look at Indicator 6.4.2. Indicator 6.4.2 measures water stress and must be reported on regularly by all countries adopting the SDGs. Stress is expressed as the percentage of available water resources. In the equation, TFWW is total freshwater withdrawals. TRWR is total freshwater resources, and EFR is the environmental flow requirement. In establishing this indicator, the United Nations and FAO, which is responsible for this indicator, have redefined available fresh water as the total freshwater resources minus the amount required for ecosystems. This is huge. It indicates that countries should endeavor to meet all their extractive water requirements from the volume of available water in excess of the environmental flow requirement, thereby ensuring freshwater ecosystems have the water they need to remain functional. A guidance document has also been developed to assist countries in incorporating environmental flows into their calculations. To assist countries in the determination of environmental flow requirements, FAO, with the help of IMI, has developed a global environmental flow information system, which already includes a quantification of environmental flows for each country. Many countries, however, have expressed reluctance in using this global tool because they do not feel that national conditions are represented in sufficient detail. Many countries are therefore embarking on their own initiatives to determine national environmental flow requirements. This presents an extraordinary opportunity for international cooperation, as many countries still lack the internal capacity to conduct such assessments. But the number of countries lacking this capacity may be fewer than you think, because there are now many countries in which environmental flows are protected in national laws and regulations, and where environmental flow research is underway. Beyond the well-established environmental flow research in Australia, South Africa, the USA, and parts of Europe, many countries in South America, Eastern and Southern Africa, and Asia now have active research programs in environmental flows. It's true that many remain focused on the assessment aspects of environmental flows rather than underlying flow ecology relationships, social relationships, or implementation aspects, but the topic has established itself nevertheless, and opportunities for collaboration are there. I hope those of you interested in this will seek out literature beyond your own geographies and even reach out to researchers in new countries to explore opportunities for collaboration. There's also a new opportunity for international cooperation coming next year, linked to the 9th phase of UNESCO's International Hydrological Program. Environmental flows are one of the topics targeted in this broad-ranging initiative, and there will be activities to incentivize cooperation and better inform national governments on the topic. IPBES is going strong now following the publication of its first global assessment, and although I've not found explicit activities oriented toward environmental flows and freshwater ecosystems, the platform offers an important potential opportunity for incorporating it. This year marks the launch of the UN Decade on Ecosystem Restoration, and with environmental flows being an essential element in freshwater ecosystem restoration, they should feature in some element of the program. And then there's Future Earth, which places international cooperation across networks at the core of its mission to provide knowledge needed to support transformations towards sustainability. The world is full of opportunities to build your international network and engage in the global process of extending environmental flow science and practice and implementing the recommendations of the Global Action Agenda for Environmental Flows. But becoming engaged in these international initiatives can be challenging if you're an early career researcher. It's much easier, of course, if other members of your research group or existing networks are involved. But if not, don't give up. Look for events you might participate in to establish connections and demonstrate your interest. Make contact with other researchers you find are already involved and explore opportunities for collaboration. Some persistence may be required, but the benefits will make it all worthwhile in the end. So, that brings me to the end of my presentation. It's clear we're facing an enormous challenge in protecting water for freshwater ecosystems. The pressures are great. The science is complicated. It requires going out of our comfort zones and perhaps doing science differently than we have. It requires cooperation across the globe and being open to a plurality of ideas and approaches. It's daunting. But I hope I've also left you with a sense that it's possible, that our science is uncovering the necessary knowledge and we're developing the tools needed to apply this knowledge. Environmental flow scientists and practitioners across the world are guided by a common, self-created action agenda, and there are many international initiatives available to assist in carrying this agenda forward. And the political enabling conditions are in place in many countries and globally through Agenda 2030 and the response of nations to comply with it. Thank you very much for your attention, and I look forward to hearing your thoughts and ideas in the discussion session. That's the end of my presentation.